We are interested to know the stress-strain behavior of a material because we want to find out how the loadings we apply on the material will cause the material to deform and even fail. Normally, the stress-strain behavior of a material is determined through standard experiments. There are some excellent videos that you can find online that records the process of tensile testing or compressive testing. Therefore, I strongly encourage you to do a search and watch those videos to get a good understanding of this type of experiments. Here, I will briefly explain the procedure of a tensile experiment. For a tensile experiment, you will have a specimen of the material that you wish to test, and the specimen will come with a standard shape that will work with your testing machine. The testing portion of the specimen will have a known initial cross-sectional area, A0, and also a marked initial gauge length, L0. Sometimes there simply is a series of length marks on the specimen. And then we install this specimen into the testing machine by screwing or clamping the two ends of the specimen into the machine, and the machine starts to pull this specimen, applying tension forces on it. Then the specimen will deform under the continuous pulling and gets longer and thinner under the tension forces. And if this continues, this specimen will start necking and eventually fails. And that completes the experiment. Of course, you can do a similar compressive testing experiment, and instead of pulling the specimen, the machine will compress the specimen until it fails. During the experiment, at different time points, the machine records the loading applied at that point. From here, we can calculate the average normal stress, sigma equals to tensile force divided by the cross-sectional area. Also, the changing gauge length can be recorded at the same time, and from here, we can calculate the normal strain, epsilon, which is the new length, minus the old length divided by the original length. And both the normal stress and normal strain are functions of time, and we can plot these two variables and get the stress-strain diagram that can help us visualize the stress-strain behavior. Now, if you pay attention, you will realize that over time, both the cross-sectional area and the gauge length are continuously changing. So these two equations cannot really give us the true stress and strain at a given time. That is correct. The stress calculated this way by assuming a constant cross-sectional area is called nominal or engineering stress, and the strain calculated this way is called nominal or engineering strain. And the diagram made this way is called a conventional stress-strain diagram. Since these diagrams are constructed following the same calculation rule, the engineers will interpret them with the same understanding and still get the needed information. And of course, if needed, a true stress-strain diagram can also be constructed by correcting the changing cross-sectional area and gauge length of the specimen. Let's look at an example of a typical conventional stress-strain diagram. The x-axis is normally the strain, and the y-axis normally represents the stress. Initially, when the stress increases, the strain will increase proportionally. On the graph, it is represented by a straight line with constant slope. This behavior will stop once the stress reaches the proportional limit, sigma PL. And as the stress continues to increase, it reaches a point called yield stress, indicating that the material starts yielding. That means before this point, the material is going through elastic behavior. And if we unload the specimen from the machine, it is able to restore the elongation and return to its original length and shape. But after the yield point, the material enters plastic behavior, which means that any deformation after this point is not fully restored. The deformation is permanent. During yielding, there might be a small decrease in the stress and a period where the material is deforming even without any increase in the stress. After yielding ends, we can add more loading to the specimen and it will continue to deform up to a point of an ultimate stress, sigma U. This period is called strain hardening. After this is when necking starts to occur, and the material will fail eventually at the failure stress. And that completes the stress-strain diagram. If you wonder, why is the ultimate stress higher than the failure stress? Shouldn't it be the other way around? That's correct. Don't forget, this is the conventional stress-strain diagram. On the true stress-strain diagram, the failure stress is indeed the highest stress the material experiences. Again, shown here is just an example. Different materials, for example, brittle versus ductile materials, might have different diagrams, and a compressive diagram will look different than a tensile diagram. Now let's further analyze the stress-strain diagram. Based on the stress-strain diagrams of different materials, a simple classification of materials is ductile material and brittle material. In general, ductile material can be subjected to large strains before rupture. In other words, they can exhibit large deformation before failing. They normally exhibit higher resistance to tensile stress than compressive stress. Brittle materials, on the other hand, exhibits little or no yielding, in other words, no deformation before failure. They normally show high resistance to compressive stress than tensile stress. On this diagram, this proportional region is of special interest. It shows that the deformation of the material has a linear relation with the normal stress. The slope of this line is known as Young's modulus, E, which is an important and inherent parameter for material mechanical property like density. It can also be called as the modulus of elasticity. This linear relation can then be written as sigma equals to E times epsilon, and this is known as the Hooke's law. Sometimes the yield stress is not very clear on a stress-strain diagram. For this type of diagrams, we can use a 0.2% offset method to determine its yield stress. This means that we read 0.2% on the strain axis, which is a strain of 0.002. And from here, we draw a line that is parallel to the straight line on the diagram, and where this line intercepts with the diagram is considered as the yield stress. Let's look at the stress-strain diagram for a ductile material. If we want to increase the yield point for this material, we can do some mechanical modification called strain hardening. We can load the material to a point that it passes its original yield stress, and at this point, the material will already have permanent deformation. When we unload it, it will not follow the original diagram, because keep in mind, there will be deformation that cannot be fully restored, but instead, it will behave this way. And this will permanently change the stress-strain behavior of this material. And this is the new stress-strain diagram for the material. As you can see, the yield stress has indeed been increased. During unloading, the part of deformation that the material was able to restore is called elastic recovery, and the deformation that cannot be restored is called permanent set. During deformation, the material will absorb energy and store the energy internally through its volume. This energy is called strain energy, and strain energy per unit volume of the material is called strain energy density, denoted by U. Mathematically, the strain energy density at any given point equals to the integration of the stress-strain diagram, or the area under the curve. Of significance is the modulus of resilience, which is the strain energy density at the proportional limit. It equals to the area of the triangle, which equals to 1/2 times sigma PL times epsilon PL. The modulus of resilience is an important parameter that describes how much energy the material can absorb without any permanent deformation. Another important parameter is modulus of toughness, UT, which indicates the amount of total energy that the material can absorb before failing. And mathematically, it is calculated by integrating the entire stress-strain diagram, or calculate the area under the entire curve.